Hello again to folks just joining us. We're going to be getting started with the software management at MSI tutorial in just about 1 minute, targeting 3 after the hour for our start. All right, 3 after the hour. So we'll go ahead and get started here. So welcome everyone to MSI's software management at MSI tutorial for the spring semester 2026. I am Nick. I will be your instructor today. I'm one of the staff members at MSI who is responsible for installing and managing our user-facing software library. And I'm going to try and pass along some of the skills and wisdom that I have sort of derived from dealing with that software library so that folks can be empowered to manage their own software. And helping out today is Angel, who will be monitoring the chat. I'll also be keeping an eye on the chat. Any questions that come up, please feel free to post them in there. I think we're also a small enough group that if you're comfortable doing so, you could come off mute and ask a question, and that should be fairly non-disruptive as well for us. So the first thing I'll do is the help desk has asked me for all of these virtual sessions because I can't physically point you to where the help desk is to drop in chat for everyone the link that gives you information about how to contact the help desk, where it is. That's your first point of contact if you are having any difficulty with accessing MSI or with running the workflows on it. And they'll help you to either resolve the issue or get connected to one of our staff members who can help you to resolve it. And then another link that I will post for everyone is the material that we're going to be covering today. This is at the UMN GitHub, so you will have to authenticate with your UMN ID in order to log into that. But once you do so, this is the sort of software carpentry style breakdown of all of the topics that we're covering today, with some useful descriptive text, as well as the specific examples that we're going to be going through. So very good for following along, very good for reviewing after the fact is the hope with this material. So getting into the material itself, start off with a couple of definitions for terms that are going to come up pretty commonly as we're discussing things today. There is the concept of a software package, which is for our purposes here, a single program or toolkit, something like TensorFlow or Gromax or Hammer, things like these. And packages may have many different versions of them available, but we're talking about package as the umbrella term for the sort of software project that may release multiple versions. Then broadening the scope from that, there is this concept of a software environment, which is, for our purposes here, a set of packages that are working together to create a pipeline or workflow where you might have a few different packages that may pass information or files between them. You might have to run some steps manually. Some steps might be automatic. But those software packages are all part of that software environment that you are using. Um, and then dependency is an important concept when we're thinking about building software, which is a package that is required in order to build or use another second package. For example, the FFTW library is a dependency of GROMACS. So you must install and have present FFTW in order to build and run GROMACS. Okay, so those are our common terms here. We'll be using them often. So why even have this tutorial, right? MSI has a large library of software that we try to maintain in good working order for folks. But it's not always possible for us to meet the specific needs of particular research groups or particular workflows within those research groups. There are often very rapid update cycles for things that are particularly cutting edge. For instance, a lot of machine learning workflows right now might have multiple releases a week, and there are a lot of machine learning workflows. And so MSI is not really able to manage the installation and maintenance of keeping all of those up to date at a good pace. And so for situations like that, it starts to become useful for researchers and research groups to have some internal expertise for managing their own software. And if you are a little more self-reliant with some of these software skills, it can help you to avoid some common pain points. As I've highlighted at the start of our material here, for instance, if you find yourself needing to validate results against a previously published paper that used a specific version of some package or packages, but there are conflicts because those old versions conflict with the latest versions that the student is using for their own work. And that's not necessarily something that the module library that we provide can accommodate, and so the student might need to navigate that a little bit on their own, particularly for especially old papers that they're trying to reproduce. Also, we try to maintain a long back catalog for our software modules, but it's just not always possible for us to preserve indefinitely all of the software in the state that it was in when you used it 10 to 15 years ago. So it can be useful to maintain documentation and materials and the knowledge of how to use them if you need to reinstall a piece of software exactly how it was when you originally ran a simulation for a paper to check up on a possible error that a journal contacts you about. Or in some cases, we have more like practical legal limitations where there are software packages with licensing considerations where MSI is not permitted to run the software, where a single research group would need to be managing it on their own in order to fulfill the license terms for that particular piece of software. And so you would need to know how to work with that on your own. And so we're going to build up some comfort and some tools that will allow you to address that kind of situation rather by managing your own software and knowing how to do so in a sane and scalable way. And so what we're going to be doing broadly is trying to keep the packages that we install as independent as possible. Some stuff has dependencies, so it's impossible to avoid any and all coupling, but if we can minimize it, that will prevent the situation where your entire software environment depends on like a single linchpin piece of software accidentally, that breaks, and then the rest of the environment breaks, and you can't do anything until it's all fixed. So we're going to try and keep things separate, so at least individual components will keep working if something goes wrong with a different one. Going to emphasize keeping enough documentation that it's easy to stand things back up if you need to reinstall it in a new environment, say on a different computing cluster, or if you're maybe getting started on Blackwell here in the not too distant future, you might need to reinstall something there. And also, we like to reduce the dependence of groups who have an interest in this on the HPC support staff, like myself and Angel. There's only a few of us who handle this type of software curation. And so we try our best to keep things in a good working order for everyone, but we're just not going to be able to catch all of the edge cases. And so it's good where possible for folks to have that internal expertise, so we don't have to show up and get fully up to speed on what you're doing in order to fix what could be a relatively small error if you internally know how to deal with it. So it just reduces downtime potentially if you have internal expertise within your group. Then let me share my screen here. So we're going to start getting into some examples for how this is all orchestrated at MSI and other similar computing centers. Yes, we'll allow Zoom to share my screen. All right. So I believe I am sharing. Is the text size good on this window? Are folks able to read this? You get a thumbs up or a yes in the chat.
Yep.
Yep. All right. A couple of confirmations. Excellent. Zoom is trying to obstruct my view of everything. Alrighty. So I am right now working on Agate. I'm logged into one of the login nodes here. If you'd like to follow along, you can get a session via Open On Demand or your terminal of choice to get a connection to Agate. The examples that we're working with today, if you're following along, will behave differently if you're running them on your local machine. And I can't guarantee that we'll be able to help with that either. So yeah, following along, be on Agate with me here. But when we are logged in to the cluster, we are in a new bash session, the shell that we are running in. And when we log in, we're automatically dropped into an existing software environment. We have a set of programs that are available to us already that allow us to interact with the system. I've used a couple of them here. LS will show you the contents of stuff. Hostname will tell you the name of the node that you're on. SSH, echo, these types of commands are all programs that are immediately available in the session that we're in. And the way that the shell is locating that software, where it knows where the hostname program exists, is the same way that it's going to locate the research software that we're going to be installing, which is through checking relevant environment variables. And environment variables in a bash session are variables that are set within the context of the bash shell that we're running. Usually they're all caps. And we can get a list of all of the, excuse me, environment variables, aliases, and functions that are defined with the env command for env. Just run this here. It's going to be a lot of output. Toggle my scrolling to work. We can see that we've got lots and lots of these all caps variables that are defined in our session. Some of them may be familiar to you, some of them may be a little more obscure. But we're going to be interacting with just a couple of them for our purposes today, because we only need to tweak a couple in order to make software visible, and just a couple more to make sure that software is able to find its dependencies in a clean way. So I'll go ahead and clear that. And in particular, the primary variable that we're going to be looking at in our bash environment is the path variable. So like any other variable in bash, if we want to see the current value of a variable, we can say echo and prefix with a $sign, the name of the variable. And this will show how this variable is currently defined. This is colon separated list of different paths. Yours may look different than mine if you're following along. We should have at least this middle section in common that's referring to system paths. I have some additional stuff that's referring to home directories, because I have customized my environment a little bit, and we'll show you how to do that as well if it's convenient for your workflows. And we can look at what's inside one of these directories with ls. If we say ls/user/bin, we see we've got a bunch of different executables. The way ls is categorizing things, the asterisk means this is an executable file. Then we have some links as well, which are often just renamed versions of other executables that are in here. There's a lot of programs that are provided by the operating system happen to live in /user/bin. There's an awful lot of them in there, though, and so if you're looking to see where a particular program lives, it is not convenient to say, well, I'm going to ls each of those entries in path and then just visually search for it. You could grep it, you could get fancy with your shell utilization. But we've got a tool that allows us to answer more directly, when I run a program, what is the location on disk of that program? And that command that we can use is which. And if we look at, say, ls, for instance, where does the ls program live? We see, for me, I've got an alias, which is sort of prefixed to our output here. You may or may not have customized your ls behavior to see something similar. But we see that eventually this is resolving to user bin ls. So ls was somewhere in this output that we were seeing here. And in fact, ls might exist in some of these other locations on the path as well. I sort of hope it doesn't, so I don't know why it would be installed in these custom locations that I'm using. But in principle, there's no reason that you can't have the same program, program by the same name installed in multiple locations that you include on your path. You can put anything you like in a directory if you own it. So you can generate as many things called ls that are programs as you want and put them in these different locations. And the reason which is so helpful for us is it tells you of all of the things that might be named ls in all of these that are executables, which of those is actually being run when I type ls. And it points us to our particular ls here. And the way that's resolved is it looks in each of the entries, starting from the first one, until it finds an executable ls in the first entry. And then it stops. So we found it in user bin here, which is about halfway through our colon separated list, and stops there. It doesn't check further in any of these. So we might have a bunch of things named ls and the rest of that, but it's not being found for this particular example. And we know that we don't have anything named ls in these previous paths. Now we can say, all right, so maybe I want to run a piece of research software and I'm curious where that is installed. So maybe I want to run mother. It'll delay on my typing there. So I can say which mother. And right now, I don't have any software by that name currently installed or available, and so which says as much. There's no mother in the currently defined path. Now, if I happen to know the location of an executable named mother that will do what I want, I am able to modify the path environment variable to point to it. So let's say that I just knew off the top of my head the location of a mother executable, and I want to append that to the end of path. So I'm going to say export path is equal to the current value of path, then colon, and then I'll put in my new path. And it's important to do it this way where you reference the previous value of path rather than trying to type out the whole thing or just including another completely different list of directories, because you can break your shell and have to log out and log back in again if you're not careful to use this format. But we'll go ahead and type this location. So it's in software install manual mother /bin, which is not a reasonable thing to know off the top of your head, but we'll pretend that it is here. And then if I echo path, I can see the previous value of path and then colon this new value appended to the end of my list here after a colon. Now, when I say which mother, I am pointed to an executable that exists in that directory, which means that if I want to run mother, getting perhaps the version information, I am allowed to do so. So in principle, this is sort of the core of what we're going to be doing today, is we're going to put software somewhere. We're going to remember where we put it, and we're going to indicate to bash how to find it where we put it by modifying this path variable and maybe a couple other supporting variables as we continue. Now let me intentionally elicit an error here to demonstrate why we don't manually edit path like this very frequently. So let's say that I did export path equals, if I could type that would be nice. And I will forget here to include the previous value of path. And so when I run this, so ls, see what's going on. I don't have ls in my path anymore because we don't have user bin there. Uh-oh. Are we sure? And which tells me that I still have the alias for ls, but it's not able to point to a particular location. And you'll find under these conditions that there are a lot of things that are not working because most of these pieces of software that we use to navigate the shell are no longer available. So if I want to recover this, I could say export path equal, because I still have this on my screen. I could copy and paste this value, put it back. Often you don't have that previous value on screen, so it's not trivial to recover it. I'm able to ls again after fixing that. Usually the solve for mangling the path variable is to log out and log back in again. You get a fresh environment and your mistakes are forgiven. But we're now reset to the initial state for path when we had logged in, because I did not include that mother location. So now there's still no mother available, and as a result, I can't run that software. So if we don't want to modify path manually like that, then how do we want to engage with these things? And we'll mostly today be looking at a method using environment modules, where we can run a command like module load mother 1.1. Goodness, I can't type today. This is going to be rough. And then I can see mother present in the environment. I can run mother. And I didn't have to manually fiddle with path at all. And if I want to undo this change, I can say module unload mother. And mother is no longer available in path. And we can see using another module subcommand now what versions of mother are available on the system. Because you won't off the top of your head know to type, mother 1.48.1-Rocky 8. That's a sort of MSI unique versioning scheme here. So we say module avail mother, and we see that we've got a variety of different versions available in a couple of different contexts. And we were loading this particular one by its full name. If we don't include a search term to module avail, it will list all of the modules that are currently available. So we'll just go ahead and run that to give a quick sense for the scope of the software that is available on the system. We've got closing it on 3,000 individual modules that would like each be a line or a particular package plus version entry on this. So there's lots of stuff here. And so if you have a particular piece of software that you want to run, like MATLAB, module avail MATLAB, you can see all of the versions that we currently have available for this going back to 2010. Now, the modules that we're seeing via the module avail, whether or not we're including these search terms, are installed system-wide. Anyone on the cluster can use these pieces of software with a couple of licensing exceptions for things that require special permissions or license agreements, but are included on this list, like a Gaussian or something. And seeing our software library here points to a category of cases where you might not want to install software yourself and avoid some of the stuff that we're going to be discussing in the material today. If there's a package that you know that would be useful not only for you, but for other research groups as well, in those cases, it can be an efficient time savings to flag that for MSI to say, hey, there's this piece of software that I think a lot of folks would want. Could you get that installed as a module? And that way we don't all have to maintain our internal expertise on installing that. And we'll evaluate those requests to see how reasonable that is. But that's sort of why we provide these modules at all, is because if 100 groups all want to install MATLAB of a particular version, it saves a lot of the universities and researchers' time for us to just do it once versus it being done 100 times. I've got a current link to the page where you can. Oh, that's at the help desk page now. So from that help desk page that I linked, and I'll link it again because I don't know if we've had new folks join here. there is a submit a ticket tab down at the bottom where you can choose the ticket type. And one of those categories is a software purchase request. That should say a software install request because it's not always something to be purchased. But if you check that software request option, then it will prompt you for some information specific to requesting the software. And then that will be passed along to staff who will evaluate the suitability of that piece of software for installation as a module. So be aware that that option does definitely still exist where it makes sense. But this would be a pretty short tutorial if I just said, oh, you can request whatever you want that's justified, and you don't have to do anything else. So let's get into how we might ourselves create our own module files to support specific research within our particular groups and domains. Figure this out. Then ls. So I've got in my home directory this module files.local directory that I use for software that I install myself for use only by myself. You could have an equivalent directory that is in your project directory if the software scope is intended to be used by your whole group. But we'll be looking at doing stuff in our personal home directories today for the purposes of our tutorial. So if I didn't have this, I could make this directory with mkdir. And in fact, I'm going to make a subdirectory in there for our first new module file. So we'll say module files.local. And then I want to create a hello world module file that we can use to demonstrate some of the fundamental moving parts here. And then I am going to, with a text editor, open up a new file inside of hello world called 1.0. I'm using Nano here because it is tutorial friendly, but there's no requirements to use any particular text editor for working with module files. Emacs, Vim, Nano, these will all work just fine depending on your preference. So if we go ahead and drop ourselves into the text editor, the first thing we'll need to do to make this a module file rather than just any old file named 1.0 is to put what is called the magic cookie at the very start of the file, which is hashtag, #, or octothorpe, depending on how old you are in your first encounter with this character, followed by %, followed by capitalized module. And the module command is going to look for this magic cookie at the start of files that we point it towards to know if a particular file is a module file that needs to be parsed as such. Now, the contents of the module file for our the deployment of the module command that we have here at MSI is a TCL script. So we can add whatever TCL we like in here to run. This is a hello world, so it should run hello world. So we'll just say system echo hello world, where I'm telling TCL to pass back to bash the command echo hello world, and that will be when we engage with this module file. So I'll go ahead and just leave our hello world example here. Control X exit, confirm saving, enter to confirm the file name. And then we'll need to point our module command towards modulefiles.local to indicate that we've got software installed there that it should be aware of. To do this, we can say module use, and then we give it the location of the modulefiles.local directory. And what that's doing is that's modifying another of these environment variables called module path. which is a colon separated list of places that module files are located. And when we say module use, it appends that to the start of our list. So now I can say module avail hello world. And because we've just created this directory in this file, we have maybe a little bit more context for what we are seeing in our avail output here, where we have a path that indicates the location of the folder we pointed to with module use, which itself contains one or more subdirectories that are named after the software package that we want. Then each of those subdirectories may contain one or more module files that are named after the specific version that we are referencing here. So our hello world is our 1.0 version. So 1.0 is the name of the file contained in the folder hello world, which is then contained in a folder that contains a bunch of module files. Just for context, I've got a couple of things in here that represent other pieces of software that I like to load as these local personal modules. So it's visible to avail, so we can go ahead and say module load hello world. And what that does is when we say module load, it runs the contents of the hello world module that we are choosing to load. Now, I just accidentally done something that we will want to note here. So I did not specify a version after saying hello world, but it automatically loaded the 1.0 version that we had created. It's the only one that's available, and it's therefore the first that appears on this output. So it is treated as the implicit default for this module. So if you don't specify a version, but you specify a package name, when you say module load or module show or any of our other commands, it's going to grab the first entry for situations where a default is not defined, and where a default is defined, it will grab the default from the first directory here. So we might have a default defined if we're not using module files.local in this manual Mongi directory, and then have a bunch of other module versions defined below. It's the default defined here that's going to be picked up if you don't specify a version, which can get confusing because sometimes defaults are defined in multiple places as sort of a holdover from previous organizations of the system, but it's only the first time that you see default in our list of directories where it's going to be respected. Say module list. Why do I have a GCC module loaded? Oh, it was auto-loaded with mother. I didn't unload it. Okay, but we can see with module list another module subcommand, which shows all of the currently loaded modules that we have hello world 1.0 currently loaded as well. Now I can say module unload hello world, and that runs the contents of it again, which may be a little confusing, but we'll see how some module specific TCL bindings make that work in our favor. And if I module list now, hello world is gone from that. And in fact, I'm going to module purge right now, which is the subcommand for unloading all of your currently loaded modules. I don't need GCC 11 hanging out right now. It's just going to clutter up our output. Now if I module list, it tells me that no module files are currently loaded. All right, so we made a little TCL script that can say hello world every time we load or unload it with module, but that's not the most useful for our purposes here. So let's make this do a module thing for us and modify the path variable. So local hello world 1.0. Open that back up with our text editor of choice. Go ahead and get rid of this because I don't need that to be printed every time. And we'll make this a more module-y module file by having it use the prepend path function here, which requires us to specify an environment variable, in this case, path, and then we're going to specify an entry to be prepended to that. It's called prepend path in this case because it's being treated like path as it's going to treat this as a colon separated list of strings. So we're going to add a colon separated entry to the beginning of the environment variable path. And let's use our mother example again. Software install manual mother 1.4.1/bin. And the prepend path, this is adding this particular directory to the start of path. If we wanted to, we could also use an equivalent or almost equivalent command append path, which takes the same form of arguments here, which would put this string at the end of the variable that we provide. But we'll go ahead and use prepend here. It's more frequently what you want to do. And then we'll go ahead and exit out, just confirm saving, confirm my file name. Now, when I module load hello world, I don't get hello world printed anymore. But I can run mother now. And if I echo path, I see that I've got this modification to my path right at the beginning here. And which mother points me to the mother executable that lives within that directory. And now if I say module unload mother, say, now why is it doing that? This is not expected behavior. Oh, because I didn't call it mother. So I need to module unload hello world, our conveniently named module. Now, if I say which mother, there's no mother in my modified path. And our mother entry has been removed after I ran module unload on the actual module that we had loaded here. And the fact that unload undoes the prepend path is the convenience that we get for using the module specific TCL bindings. Things like prepend path, there's a set env for setting environment variables and a variety of other bindings that you can use in module files that they perform an operation in one direction when you load the module, and they perform it in the opposing direction when you unload or purge the module. So whatever we have defined in our Hello World 1.0 module file is applied to our environment when we load it, and then it's undone when we unload it. And so we don't have to manually modify path, we just have to have our module file written correctly. All right. So that's maybe a good coverage of fundamentals of module files. What questions do folks have looking at the module file example that we've seen here before we move on to a more concrete software build? And again, questions can go in the chat or you can come on mic if you'd like to ask. All right. Seeing and hearing no questions right now, I'll go ahead and continue. But if questions come up, please feel free to either post them in the chat or let me know that something is confusing verbally. All right. So let's actually install a piece of software here rather than referencing an already installed piece of software. And doing this, if you're following along, you'll want to make yourself in your home directory a couple of new directories, software.install and software.source, which are going to be two directories that we use throughout this tutorial and that I'll recommend that you use. Either these or equivalent ones in your own sort of robust software workflows. So we're going to go into software.source. This is where we're going to download source code or installers, and we're going to keep documentation on how to install software there alongside that source code. And so when we're building a software, that's the first place we're going to go. So we'll go ahead and cd to software source. And let's go ahead. For our example today, I'm going to be installing Hammer. So we'll go ahead and make a directory called Hammer to hold all of our Hammer source code and instructions. And then cd into it, brand new empty directory. Then I'm going to download the source code for Hammer. Paste this link into chat so folks, if you're following along, don't have to fully type it out. But HTTP lab software 2.1 tar.gz, which is a gzip tar file, which is a common way that source code is distributed. This a single file archive that inflates into a directory. So we'll go ahead and wget that. And it takes but a moment because this is not a particularly large software package. And after that's complete, we see that we have the file that was indicated at the end of our list there. Then to inflate this the software, we can tar xvf our archive name here to extract verbosely our archive. So we'll see as it goes along the files and subdirectories that are being put into the new Hammer directory that it is inflating into. And if we ls, we see we've got this new directory here. And we'll go ahead and we'll cd into it. And we'll take a look at what is provided for us in here. Now, there are a couple of things as you get familiar with installing software that will cue you as to sort of what to do to build the software. You might initially look at things like the README or this file called install for some documentation from the developers about how to build and run their software package. And there's this configure executable in here, which will flag for us, again, as we build more experience. This is probably something that uses the GNU make workflow, where you run configure, which is a step that has the script figure out the environment of your system and sort of check to make sure that it's suitable to build the software. And as output, it will produce a make file. That makefile provides the actual instructions for building the software that you pass to the compiler by saying make after the makefile is created. And then you say make install after that to the software is built by make, and then you install it to its final location with that final command. So seeing the presence of configure here indicates to us we're probably going to run some form of configure, some form of make install, which is the GNU software compilation and installation workflow. And if we look at the install documentation to sort of reassure ourselves that we're not going off on a wild goose chase here, the brief installation instructions do indeed say that we are well on our way. We've already gotten to our CD hammer, and then we're going to be running configure make. They recommend a make check step, and make install. They have an optional easel tool installation that we could do if we wanted to. Now they'll often have more detailed installation instructions on some web documentation, or they're pointing us to the user guide.pdf here, which we can't interact with so easily on the command line. But that information, if you go to the Hammer website, you'll be able to access it. But this won't always be a fully self-contained set of instructions in here. With Hammer it is, which is nice. That's one of the reasons that we use it for this example. But since we're already to this stage, we'll go ahead and we will start off by exploring our configure step. We're not going to immediately just run configure as they've recommended here. We will first run configure with the help flag to see what sort of behavior configure has and how we can modify it as we might need to. So we will need to modify configure a little bit as we proceed. And we can see that there are a fairly robust number of things that we can do to influence how configure runs. The one that we're going to be particularly interested in today is this prefix flag under installation directories, which lets us change the location that the software is installed to when we run make install. So right now this defaults to /user/local. Which is not a place that users on MSI are able to install software. This is owned by the system, and we don't have write permissions there. So we have to pick somewhere else where we can actually install software, which is going to be that software.install directory that we made just a little while ago. Now, you can sort of fine-tune subdirectories of that if you are so inclined. I very rarely engage with these, but it may be relevant to your workflow, so be aware that you can change the locations of the bin, include lib, var, subdirectories of the software if that is relevant to you. But for today, we're just going to point and say that this is something that exists. And there are optional features that we can enable or disable to get different parallelization or instruction set options, which again, we're just going to point to today and say that if you're building a piece of software and you want it to be performant, you should consult the developer's documentation for exactly how these are implemented for that software and whether they would be useful to you for running it at MSI. And there are a variety of environment variables that we can set as well to influence how the software is built. This is a code that is primarily written in C, I believe. If we look at the source here, we have a lot of .c and .h files, so this is C code. So the C compiler and C flags compiler can be very influential to how this is built. And in fact, let's make sure that we're setting a sane C compiler for this. Go ahead and clear. Just make sure I have a clear environment. All right. So we when we're building software from source like this, often, but not always, using the compiler that is bundled with the operating system um, can generate dependencies from the code you're running back to the operating system. Right now, we do have the GCC compiler available here. If I say which GCC, there is one available in user bin. And we could use that to build our software here. The reason that we don't want to do that is we want to have our code built by something that is not tightly coupled to the operating system, which is currently Rocky Linux 8. MSI is required to update our operating system as security patches become available and as it goes out of support. And we're actually looking to move away from Rocky 8 for reasons of it being out of support sometime later this calendar year. And if we use the GCC bundled with Rocky 8 to build our code, it might not work on Rocky 9 or Rocky 10. So we want to use something that was built to be portable. MSI provides a variety of GCC compilers that are independent from what is available on the system, and we can pick one of these to load instead. And as long as this compiler is still available, any dependencies that are created from our new module here would be back to this compiler rather than to the operating system, and so should be less impacted by upgrades to the operating system. It makes your software more robust in effect. So we'll go ahead and module load. I will pick, just based on tradition, GCC 7.2.0 here, which is just what we've been using for this tutorial for a while. I know that it works and runs relatively quickly. Say which GCC to make sure that we're picking this up here. And there were those influential environment variables that we had seen in order to point our configure to the particular compiler that we want to use. So let's make sure that we're doing that. Let's say that I want to say CC is equal to, and I'll use a little bash built in here to evaluate the output of which GCC. So I don't have to copy and paste in this, this string or type it out, $ parentheses, which GCC will evaluate to this. And so now if I echo CC, we get the location of that particular compiler. And so maybe that's all that we want to do for customizing this particular build. So we can say, now we'll run the configure set /configure. And we want to set a prefix because this will change the install location. Remember, it was defaulting to that user local, which we don't have write permissions to. So we'll say prefix equals my home directory / and this is where we're going to start using that software.install directory that I made. /hammer /3.2.1. And when I run this, it's going to produce a good amount of output on the screen. So I'll pause for a second if folks are typing along. But it's going to start probing the system, checking if the C compiler exists, does it work, checking for a bunch of different features and functions within the C compiler. And then finally, it summarizes sort of anything that was detected or set at the end here, which some configure scripts are configured to do. Don't get an error or any concerning output here that says maybe we should go back and try it again. So we can just immediately go to utilize the newly created makefile here, which is what configure made in addition to this config.log file. And in order to use this makefile, if there's a capital M makefile in the directory that you're in, all you have to do in order to use it is run the make command, and it will start building software as described in there. Now you can write your own make files for software that you are developing yourself. Um, that goes beyond the scope of our workshop today, but it is certainly possible to do. It just the complexity of it scales pretty quickly as your code picks up dependencies and additional executables. And that's why we'll see a lot of projects that use something like configure or CMake or some similar tool to handle the construction of a make file that will work on the current system. And so this is where the actual compilation is happening. We're seeing these object files being built, um, and then these different executables as well. ls, you can see them in source now. Where before we had just a bunch of .c and .h files, we've now got some .o files, some asterisk executable files. This is what was just built within the source directory. But they're all sort of mixed in there, and it's not very convenient to use them from this location. And so we're going to run a final step, make install, which will sort of deploy them to the location that we specified using that prefix command, that subdirectory of software.install. And this doesn't take very long compared to compilation because all it is doing is copying files and setting permissions into the specified location. So now if I ls software.install or 3.2.1, I see I've got a bin and a share directory in there. Inside bin, here's where all of our executables live. And if we look inside share, we've got these man and man1 subdirectories, which correspond to man pages for these different tools, which is one method for viewing documentation for these files. So we've built and deployed the executables and some associated documentation alongside with our configure, make install workflow. All right, so we've installed the software. Now let's make ourselves a module file that points to it. So we'll go ahead and make ourselves a new directory in module files.local called hammer. And then inside this, we will create a new file with nano called 3.2.1. And we will start off again with our magic cookie for the module file. And then we'll do two things in here. We'll say module load GCC 2.0. And we will prepend path. And then I'll type my full home directory here, pointing to hammer 3.2.1 / bin inside software.install. Now we've added this additional component here. We've seen prepend path before. We're just changing the value of this to be relevant to something we installed a moment ago. But we're also loading the GCC module that we built with. And in this case, that means we're treating this GCC module as a dependency of Hammer. When we run module load Hammer 3.2.1, it's going to load GCC 7.2.0, and we'll make, in that way, the environment that we are running Hammer in the same as the environment that we built it in. Now that's of very importance for different software packages. Hammer actually behaves pretty well without having its compiler loaded, but that's not something that you should always guarantee. So just a sort of the safe default is if you needed to load a compiler or maybe some other dependency libraries at build time, you should also load them here at runtime unless you know that you don't have to. I mean, you can always experiment and see if something's missing in terms of a software dependency. You'll most frequently get errors saying, library missing. The software is not going to give you wrong output. It will just not work. So if you want, for some reason, to pare down your module file, you can try eliminating a dependency and see if things are still behaving themselves. But this will be our module file here for Hammer. So go ahead and exit, save, confirm that file name. And we can say module avail Hammer. We see there are some system hammers that are installed. But we've got at the top of our list here in module files.local hammer 3.2.1. We can say now module load hammer. And if we wanted to stop there, we could do so because this is our implicit default, our first of 3 directories that are indicated by module avail. Or we could type module load hammer 3.2.1. And then if I look for the location of nhammer, with which I see in my software.install, I've got nhammer available there. Now, you might note that we have introduced intentionally for purpose of example a naming conflict here, where we've got 2 different modules that are named Hammer 3.2.1. And in sort of a similar way compared to how we've been seeing path and other module associated components work, the first one listed is going to be the one that is engaged with when you don't provide any additional specificity. So if I simply say module load hammer 3.2.1, when there are 2 modules by that name, the first one listed is the one that's loaded. Now, we would typically want to avoid this by not having a naming conflict here. We might name this hammer 3.2.1 - local or something, and that way we could load this by its particular version name that would be distinct from this other particular version name. But sometimes, for whatever reason, we don't want to change that naming scheme. And if we want to load this later module here, we could give the full path to the module file, including the directory that is located in. So we could say module load, then I would copy and paste in that directory / hammer 3.2.1, because what we're doing here is we're saying load this particular module file at this particular location. And now we get nhammer from that module instead of the module that we had just installed. All right, so we've installed a module. We've chosen a conflicting name for it. We can load it, unload it. Suppose I should demonstrate module load 2.1. Should demonstrate that our software actually runs at least enough to produce the help menu for nhammer. Created valid executables with this. An important part of installing software is that it runs when it's done. We've got that here. Module purge. And now that we've verified that the software is working, let's say that I've done some additional testing on this. I'd want to record exactly what I did in order to make sure I can build it again should I need to do so. Now, if you're doing this sort of all in the same session, the history command can be quite useful for this. which will give you the last however many um, commands that you have run, and you can pick out the ones from the most recent here, for downloading, inflating, setting our environment variables, uh, and pull together your bit of documentation based on that. You can see what was actually done. Then once you've got that information, we are going to, inside our software.source directory, we're going to create under Hammer something called readme.recipes, which is going to contain the build instructions for any of the different Hammer versions that I've built. And I might sign it with my particular name. That's not maybe the most interesting thing when it's in your own home directory, but if you're doing this for a group, it can be useful to know who to contact if something weird is happening. So it's Hammer 3.2.1 with GCC 7.2.0, just as a quick descriptive blurb here, because I might have a bunch of these entries in my recipes file as I build a bunch of different versions of Hammer over time. And then, for the sake of saving myself some typing here, I'm going to just copy from the course material the information that I would have grabbed from the history command there, where I have my download wget command, the command I use to inflate Hammer, move into its directory, we load our dependency, we set our C compiler to be the GCC that we just loaded. We configure using a custom prefix for our install location. Then we want run make, and we ran make install. Developers also recommended running make check to make sure everything was working at that intermediate step. I don't do that for tutorials, but it's something that I do recommend if you are building software that is intended for actual research use. It just takes a little while to run, and so is not a good use of our tutorial time. So in my documentation here, if this were actual research software that I was going to be using, I would have run it, and I would recommend running it again for whoever was doing it in the future. We just didn't happen to do it today for the sake of time. And so that's sort of putting a bow on this particular module installation. We downloaded, built the software, installed it to a particular location, and created a module file that points to it that we can load and unload as we like. And exit that. And a lot of the software installation that we're going to be seeing is going to be some variation of that, where we have maybe different procedures for installing the software itself, but we're then going to be sort of taking whatever that procedure is and turning that into a module file that we can use to point to and then clear out the software from our environment with the load and unload commands. What questions do folks have after seeing our first full software install of this type?
I have a quick one.
Yes.
So in this case, you loaded GCC and then like a specific version, and you knew that you had to modify the CC environment variable. In this case, you knew that. But is there like a resource? Because there are so many variables, and sometimes it has to be that, or sometimes it's like our path, or is there somewhere that we could check which is the variable that we need to change?
Your best resource for that is almost always going to be either the build notes from whoever came before you for the particular system and software, or failing that, the developer documentation. You can read up on variables that are influential for particular tools. Like if you're always doing the GNU procedure like we've seen here with configure, make, install, you'll get comfortable quickly with a small handful of variables that are always important for that. And a slightly different set if you're using the Intel compilers, a slightly different set if you're using the AMD compilers. But there's not like a good general resource that will inform you broadly across the different installation approaches, if that makes sense. It's all fairly specific to the projects and their tool chains.
Yep, that's what I feared. Thank you.
Yeah. Yep. Other questions from folks? If not, I will, I guess, point at the example that we are that I have written out here, but that we do not explicitly cover for CMake, where we go through the same procedure for installing a package that uses CMake instead of the GNU make. CMake is a little newer and maybe a little more fashionable to use these days for building your projects from source, and has some more nice features in terms of automatically detecting dependencies of a certain type, but it's also a little more complex, and it has a different interface compared to our previous example. But it's similar enough that I'm going to let the course content here sort of speak for itself for the particular Luscus example, because we want to save time for the container demonstrations at the end using apptainer/singularity. If you do have a project that relies on CMake and you run into difficulty with it that goes beyond the scope of what's demonstrated here, definitely you can reach out to the help desk, and myself or one of my colleagues should be able to help point you in the right direction. But just wanted to point out that that exists, even though we're not going to be explicitly stepping through it today. Then I think before we get into our Anaconda and pip section here, it's probably a good time for a short break so folks can hydrate, stretch their legs, get a little caffeine. All right, folks, welcome back. Hope we're all situated and hydrated and ready to wrap up our material here. So we had just seen our first example of installing software and creating a module for it using the GNU make workflow. And I pointed to an example that would be fairly similar using another tool called CMake, which essentially replaces the configure step with CMake, which provides additional complexity that pays for some additional features that can be very helpful for building different software packages if projects decide to use it. And let's take a look then next at installing software using Anaconda and pip, which are both fairly popular pieces of software for installing both Python dependencies and particular versions of Python in the case of Anaconda, but also sort of a broadening set of research software, especially in the data science and machine learning spaces. So before we jump into the example there, because this is unfortunately a truth of the landscape we're in right now, I do have to flag that there are some licensing concerns around the use of Anaconda as of change in the Anaconda terms of service spring 2024. They no longer accommodate the free use of certain of their components that are specifically licensed components by academic researchers. So far as I know, we're 2 years later, and I still am not aware of good guidance on how to proceed using those licensed components. So what I'm going to do instead is provide some guidance on how to avoid using the licensed bits and use the open source and community managed components that the Conda tool has access to. So the Anaconda, capital A company, is the one doing licensing stuff that we have to sort of stay away from, unless your research group has a particular relationship with that company, in which case, do whatever is acceptable under those agreements. But the university does not, and indeed cannot, have such a relationship. So there's a little blurb up at the top of this page here in the material, which specifies a couple of places to avoid installing packages from. And in particular, you're going to want to make sure that in your Conda RC file, if you have been modifying this in the past, if you're a previous Conda user, that you don't have anything in here that specifies the use of those channels in like a channel priority list. I don't even specify any channel priority in my Conda RC, so this one's clean by our purposes. But if you see any of those defaults, main, Anaconda, MSys2, or R listed in here, you'll want to take those out. Then, having done that, if you use a module called MiniForge instead of any of our other Conda modules, that will guarantee that you are using something that draws from community repositories rather than these licensed ones. So that's an unfortunate reality. I do not like talking about or engaging with these sort of licensing limitations, especially with a tool like Conda here, but it's useful enough and embedded enough in workflows that we do need to discuss it and that complication around using it. So then, having made sure our Conda RC is clean, we could then, sure, we're all cleared out in terms of my environment. We could say module load MiniForge, and there's an omitted MiniForge here and notes that I'm going to make. A correction for next time. We say module load MiniForge, and then that gives us access to the Conda command. The Conda command itself is open source, so we do have access to use this as long as we're using the community channels, which MiniForge does by default. Now, the workflow that you will most often see in sort of package developers documentation is you say, oh, you've got your Conda command. Well, no, we are the developers of Pandas, say, which is a Python toolkit for working with tabular data. You want to install Pandas? Well, all you have to do is say Conda install Pandas. And that will probably install Pandas if you own the system that you are running it on and you have write access to the location where Conda is installed. But if we try that here, this is in a non-user writable directory under our common software a folder there. So this won't work for us. And even if this was your own workstation, I'd still recommend maybe not doing things this way, because if you install a bunch of different packages in this way, just installing them all into what is known as the base environment here, the one that is brought in association with our mini-forge module, then you'll run into conflicts pretty quickly. So if the only thing you're doing with this computer via Conda is using pandas, this might be fine for you, but we're going to not run that here, and we're going to install in a way that gives us the flexibility we need to install a bunch of different things. Okay. All right, there's a little Zoom UI element that was in my way that I was able to move finally, which is nice. I can see my cursor now. So what we would do instead is I'm going to define a variable for today's date that I'm going to use to tag the particular pandas environment that I'm installing. So the way I'll do that is, again, with some of this bash expansion magic, using the date command. I'd like the day, the month, and the year for this, using just the syntax for the date command. And if we echo the date, March 19th, 2026, and nice little 6-digit indicator there. And the reason I'm defining this right now is because when you install something via Conda or one of these other package managers that goes out to some separately maintained set of repositories on the internet, the result that you get when installing via a straightforward command today might be different than that same command tomorrow because those remote repositories change. Something was updated, some additional dependency was introduced or declared. And so it's important to know when something was installed in order to, if you need to reproduce it in the future or debug the reproduction of it in the future, knowing the date that it was originally created can be instrumental in the success of that, or in figuring out that it cannot succeed, which does sometimes happen when you're relying on these remote repositories. But we've already got our mini-forge module here. So we'll go ahead and write ourselves out the command that I would use to actually install the software, and then we'll talk through what those different changes are. So we're going to say conda create. Add a flag here for dash dash copy. We'll say dash p to give it a different prefix here. So we're going to say home, install pandas and date. If you wanted to get fancy with this, you could have it be a particular version of pandas dash today date or something. But for our purposes here, just knowing the date will be sufficient. And then finally, we'll say what we want to install. So our different command here versus conda install pandas, which just installs conda into whatever environment you're currently in. We're saying conda create a new environment where we're going to install pandas and any dependencies that it seems to need. And we're going to install that at this prefix, this dash p, which is a location in our software.install directory. And this dash dash copy flag, what this is doing, Conda likes to be lazy when it can be with its file downloads and copying. So if you omit this flag, then in general, when you create a new environment, it will not contain all of the original files that are required for that environment. It will contain links to where those files were first downloaded. Whether that's in some cache directory or associated with this original base directory. And that introduces a dependency that's sort of invisible to us at install time that we don't want to have to deal with later. We want this to be a self-contained environment that we can confidently load and unload without worrying about something else that might be changed and breaking it somewhere else. So we say copy. This makes a copy of those original files rather than linking to them in our prefix here. So we actually have a properly self-contained environment as best we're able. And then after all of this, you can have a list of one or more packages that you actually want to install into the environment that you are creating. So we'll go ahead and run this. I'll take just a moment as it reaches out to the CondaForge channel. This is the channel that contains the community managed software. It's unfortunately sort of less reliable and tidy compared to the default Anaconda, but it's still very functional, and we're actually allowed to use it. So that's a big selling point. Then after the environment has been solved, where Conda figures out what needs to be downloaded in order for pandas to work, we can see sort of the manifest of what's going to be grabbed, and then all of the packages that are going to be installed into this environment should we proceed. Go ahead and say Y to allow that to happen. And while we're waiting for this, that's an excellent question, Natalia. These packages that we're getting via Conda are indeed already compiled. We're getting already built executables and libraries here. And that's why we don't have to think about GCC versions here. In fact, in a lot of cases, there will be, like we have a libgcc that's being downloaded and a libgfortran that are being pulled in as dependencies for this environment. So we're not thinking about compiler versions, but Conda is thinking about those for us and putting the appropriate ones in the environment alongside pandas and the rest of its dependencies. And that's one of the nice things about Conda, I suppose, from a certain perspective. We're not needing to deal with or build from source code, but it's also potentially a negative if you need to do like very strict auditing of source code before allowing it to run on your system, for example. Because it's depending on your tolerance for risk of dubious trustworthiness, what is actually contained within any one of these binary packages. And we'll see an example with pip. All right, so we won't see for the, we don't have a pip example specifically, but pip works with a combination of source code and precompiled executables, but it handles the sourcing of those things in the background. Both Conda that we're using here and pip, which we'll talk about in a bit, are seeking to be package manager programs that are a similar level of functionality as the bundled ones with your operating system, like an apt or a yum or a DNF, which you would use to install software to the operating system if you were a sysadmin from the operating system repositories. These are like bonus repositories that someone else owns using different framework that you can use to install different software. And the intended interface for those is you have straightforward commands that you can say, you know, whatever repository manager, install this list of software, and it gets all of them and their dependencies for you. And so that's what Conda has done for us in the background here. Now, it tells us here that in order to use this environment, we would have to run conda activate and then point to the location of this path. Please don't follow this instruction. It's fine sometimes to do, but in order to use the conda command in this way, you need to first run conda init, which puts a block of code in your bash rc file. And that block of code can cause other things unrelated to conda to break, especially when they rely on the existence of a particular version of Python. So we've seen this break things like open on demand for some folks, other graphical applications. There was a particularly bad period when people who had done conda init with a certain version of conda could not log into our systems because it would immediately break on trying to find a Python to initialize their session. So we're not going to do this. And I would recommend avoiding it just for safety in a cluster computing environment like we have. We are going to need to activate the environment for just a moment to get a snapshot of what's actually inside of it. And if you need to activate an environment sort of like this without using conda, there is the source activate command where this this does the same thing but doesn't require us to contaminate our bash rc with conda code. So if I source activate this, now I have access to this Python pandas environment. And I want to do that here because, as we've been discussing, we're not working with source code here, so we don't actually have like a proper input if we want to recreate this in the future. Ideally, we want to store like all of the specific packages that we installed in a particular version so we could deploy an equivalent environment at some point in the future. If you know some dependency tree has changed, we could sort of reconstruct this from scratch as it is indicated there. And to allow us to do that with the environment activated, we'll say conda and export, and I'm going to say no builds. This will truncate some information from our output here that could not be used to deploy this on a different system, say. And then I'm going to omit any lines that contain prefix, because again, those will make this a little bit less transferable. And then I'm going to redirect this output to software.source and oops, I'll say reference our today date variable, and we'll save this in a YAML file. I think this is going to fail because on pandas directory. All right, so we'll try that again after I make the software.source pandas directory, which had not existed until just this moment. And we'll recall this command and try again. And then after it is written there, we'll go ahead and just open this up to take a look at what we have written in here. And so what we have installed, or what we have describing what we installed, sort of the name of our environment, which in this case is the directory we installed it into, the channels that it installed from, that was only conda forge in this case because it didn't specify any other ones. And then all of the dependencies are indicated here with the specific version that was installed. I see a question in chat here about accessing the link there. I don't know why you would be having difficulty accessing the UMN GitHub with your university account. So far as I know, if you're able to access university resources, you should be able to access university GitHub, and this is a public page within that context. So I would ask that you submit a help ticket for that if you want to look at this later. So it's not something that I'm able to debug now. And then the session is recorded and will be up on the MSI YouTube page, usually within a matter of a week or so. And there are previous deliveries of the same material available there already. But yes, we have the list of things that were installed here at their particular versions. So we could, if we wanted to, go and install manually these different dependencies at their specific versions for this whole list to recreate what we need to from scratch. Now, we're going to not recommend recreating anything from scratch. We will, in fact, recommend using the built-in conda functionality of redeploying an environment from a YAML file. So for instance, if we wanted to, we could say conda and create, then we say -f because we want an input file. Source pandas. Then we give the location of the YAML file. And if we ran this command against this YAML file, Conda would install those packages at those versions to the location specified by name if we needed to deploy this again in the future. So this is sort of our build recipe if we need to come back to it. That in this case happens to be easily machine readable in addition to being easy to do as a summary. So we don't have to reinstall all of those things by hand. We can just say conda reinstall that set of stuff based on the spec in this file. I'm not going to do that because we just installed it already, but the conda env create from a YAML file is one way to do this. And this is really handy because you can hand this YAML file to lab mates, your PI, your collaborators, whoever. If they need to run the same code that you've been running that requires this environment, you can say, well, here's the YAML file. It's a small text file. You can email to them easily enough. And you can deploy from it using this conda env create, and then you'll be up and running with exactly the environment that I had fairly easily as well. So that's a convenience available to us with conda here. I'm going to source deactivate so that I'm no longer in the pandas environment. It gives me a deprecation warning, but we'll ignore that until and unless the conda command becomes more well-behaved, and we can recommend using it. Then, in order to turn this into a module file, first let's take a look at what was actually installed here. This was the install directory specified, and we've got, in this case, bin directory, some conda meta information, and then a variety of other subdirectories for some sort of bonus content. Include and lib are two directories that you will commonly see when installing software. Include has often header files that are referenced by compilers in order to reference the functions from other libraries. And those libraries are contained usually in a corresponding lib directory that lives parallel to the include directory referencing it. And then share has our documentation again. And then we have some sort of deployment specific conda stuff in SSL and this x86-64 directory here that we're not going to need to think too much about unless something breaks and says that it's broken in one of those directories. So this is sort of at a glance a little more complicated to engage with compared to the hammer example that we saw before, where we only had the bin and the share. But luckily for us, for the vast majority of conda environments, making a module file that utilizes this is just as simple as it was for hammer. All we have to do is add bin to the path. very occasionally for conda environments, you'll need to add the lib directory to a different environment variable called LD library path. But the way conda is architected intends to avoid needing this, and so this is only necessary in cases where, at least in my experience, where the developer has made some sort of mistake in their packaging and deployment. So we don't frequently see the need for this with conda. So let's make ourselves that module file to use this. So we'll local pandas, a new directory as you can have all of our pandas modules. Files.local will then open a text file that is named after our today date, because that's what we're using to sort of indicate the version of pandas here for our purposes. And then again, we are going to want, oops, goodness. Order is important with our magic cookie. So again, pound% module, and we can say times path, servers 3, 4, software.install. If I could type pandas, the terminal wasn't lagging too. That's weird. And so our date today was 1903. 6, and then we wanted to include the bin directory and path. That's where all of the associated executables live for this particular one. And this is generally for a conda module all we need. Now I will note a sort of special case where often you will see conda recommended as a way to create an environment that contains all of the dependencies for some other package. That's commonly something that I see on research software presented on GitHub, for instance. They'll say, you know, build this conda environment using our handy YAML file. And then after you've got that, you can download and build and run our software inside there. And something that I like to do to keep things tidy is, in that case, create our environment as I have here. But then once I download that sort of the software that depends on this environment, I'll copy any executables that it generates into the same bin directory. Then my module file is just as clean as it was. So everything that I need, the target package and all of its dependencies are now contained in the conda created environment directory here. So you can occasionally run into trouble doing that if things they care a lot about the relative paths, but very frequently you can get away with just slotting those executables in here. Exit this, confirm file name. Now, something to keep in mind with conda is that as it's constructing these environments, it's caching packages in your home directory. I mentioned a package cache is one of the locations that if you don't use that -- copy tag in copy flag rather in the create subcommand can be linked to. And we use copy in order to not need to care about what is present in those directories aside from the convenience of not having to re-download things if we can afford the storage. But if you're building a lot of conda environments or very complex ones, the contents of that cache directory can become very large, both in file size and in file count. And so you might need, in order to avoid running over your quota, to clean that out. So we can say, if we want to do that, conda clean all, and I would do a dry run right now because I don't know what I have cached currently. And this would go through and indicate what would be removed for each of these. And very frequently, because I do a lot of software installation stuff, into the dozens of gigabytes of tarballs and packages, and into the hundreds of thousands of files in here. And so for me, cleaning this out occasionally is very important so that I can actually log into my account. And so I don't think I need any of that looking at what was indicated here. I can get rid of the dry run and say just conda clean all, and it will prompt me if I want to get rid of those tarballs. The index cache, which is basically a snapshot of uh, conda forge for the set of packages that I was interested in, and the declaration of their dependencies, and then the sort of common location of all those packages that would be linked back to if I allowed things to link, not if I didn't use that copy flag. And I'm perfectly happy with all of those being removed here, because I need to not uh, yeah, run over my quota. I mean, I have used the copy flag, so this is not important to me. So go ahead and let that complete. If for some reason, and there are certain workflows that benefit from this, you want to keep your Conda cache around for longer than is convenient, or at a larger size than is convenient to store in your home directory, you can choose another location to use for the cache with a directive in your conda rc file. So if I, for instance, look in my conda rc file, I could say, all right, I would like to have my packages stored, two spaces for you. Let's say projects standard or whatever directory you wanted to use instead of your home directory. Frequently, if you're needing to save this for longer, keeping it under a project directory is probably the correct choice, because you'll likely want to keep the code around and the capability to rebuild it for as long as the project exists. And that sort of makes it the project's responsibility in terms of quota and longevity rather than your user case. If your situation is where you need this to be much larger, you could point it to scratch.global. It'll go away after 30 days. But if you don't care about keeping it for a long time, and you just are doing some strange but possible thing with Conda that generates a larger file cache or a larger number of files than you actually can contain in either your project or um, your home quotas, then putting it on Scratch just as a place for it to live temporarily can be a fine choice. And if you really wanted to, you could put it on local Scratch within a job if you need it to be fast, but you don't care about it existing for a long time, which I have not seen workflows that require that, but I can imagine that they exist. So you get the freedom with that packages DIRs to pick the location that works for you and your particular environment. So another couple pro tips for working with these content environments. Please, I and future you beg of you to not modify existing conda environments. Figure out how to install the environment you want in just a couple of quick steps in short order. Do that once, and then leave it alone after doing that. If you need an updated version of it, install it to a different directory and have it accessed by a different module. So if you install things into an existing conda environment after the remote repositories have changed assumptions about dependencies and dependency trees, that is the dependencies of those dependencies, which branches out and can be quite complex and quite unpleasant to deal with if you're dealing with someone else's curation of that. That's a good way to break your environment is to modify it even just a couple of days after you had initially installed it. So to avoid breaking things, if you need to make a change, install a new environment. Already gave you the protip about that bin directory when we were in the module file. And then for pip, the only thing that I will say about using pip with Conda um, is if you need to create an environment for software that is installed only via pip, using MiniForge to create an environment to contain it is a very approachable way to do it. There are other virtual environment options for Python, but Conda does work. You could, for instance, say, maybe I want to install NumPy via pip because there's a version that is only available via pip and not via CondaForge. Let's say for this example. To do that, let's say software install NumPy. And this might more frequently be something like a TensorFlow or some other machine learning component, which are periodically more available via pip than via Conda, but those take ages to install, and so are not suitable examples here. So we'll say we have a fictitious NumPy version that we want to install. So we're going to create this independent environment as a NumPy today date directory. And the things we want to install into it are its own Python and its own pip, and that's it. I'll go ahead and run that. This will take a moment to solve. I'm just going to create a minimal environment for running pip and Python alongside each other. And we can go ahead and say yes to that after reviewing what's going to be installed. And it takes just a moment to complete. Then once this is ready, we will use the source command to activate the environment. And then we'll use pip inside the environment to install what we need. And doing things in this way ensures that pip is installing software into the environment context that we've just created with Conda, rather than installing it to a hidden directory in our home directory, which is the default behavior. Which these other virtual environment approaches also get around. But since we're already looking at Conda, and Conda is perfectly workable for this, we'll demonstrate with Conda here as soon as the transaction is complete. So we will source activate. Look, the pip that I just installed in here is the pip that I'm going to use, and we'll say pip install NumPy. And then it's going to download and install NumPy. And this is easy as that. Source deactivate, and we could create an environment for that. Something to note though is that packages that you install this way using pip won't be captured using that conda and export command if you're doing the pip step manually. So you'd need to record that you added those manually in a recipe file alongside the YAML file. So just something to keep in mind. And then, yeah, for installing more complicated Conda environments, or for troubleshooting installation of moderately complicated environments, you can run into situations where um, we won't run this. Uh, um, Matplotlib. That's just some common things that you might create in a. We'll make this a proper example. So we'll say use the same syntax. So everything is clear. Okay. So if we were needing to install a number of packages on the command line at once, as will sometimes happen, um, it's best to, if you don't have a YAML file that includes the exact spec you're going to be installing, but you instead have a list of the different packages that you are asked to install from the developer, include everything that's intended to be installed by Conda from that list in the same Conda command. This allows Conda to do its environment solving right from the jump, using all of the available information about those packages and their dependencies. Um, and this, you may also need to specify particular versions of software. Like you need to make sure that you have, Python equal to 3 as part of this, or NumPy is equal to 2.4.3 or something, as specified in whatever developers' requirements for their environment that you're referencing. Um, and it's best, again, to include all of that information in your single conda command, because if you do it step by step, you create this with just Python and pip, and then you activate the environment and install something new, and then install something new, and then install something new on top of that, one by one with additional commands. That will lead to a higher chance of the solver failing and generating something that is not functional in the way you would like. It can also be a lot slower because as you add larger number of packages with more constraints to an existing large environment, it takes Conda a long time to rectify that, rather than waiting a moderate amount of time up front for it to figure out the appropriate answer if you just give it all of the info up front. I'm not going to run this example because it can take a little while, and again, we're making sure that we preserve our time here. But this is sort of what I would recommend if you need to install software from a list using Conda, is this approach. What questions do folks have about using Conda as our installation engine here?
I have one, if nobody else.
Yeah, absolutely.
Do you have any recommendations for making Conda environments that contain both R and Python-based software?
Sure. My honest recommendation is don't.
Okay.
But sometimes you have to. And the The unfortunate thing is that the R channel, the one that's just named lowercase r, is one of those license channels that we are not permitted to use under the current terms and conditions. So you need to rely on community provided stuff from Conda Forge, and I believe Bioconda is starting to provide some of these as well. And after the caveat of avoid installing R stuff via Conda if you can. If you must, then using the tips that we've gone over here, particularly the install everything initially at the start of your environment creation and then don't change it afterward, is going to be even more important for the R environment that you develop. Those are especially fragile via Conda. And like I said, it can work in certain cases. Sometimes it's what you'll have to do. I would recommend instead, where possible, using a containerized R solution. We'll look a little bit at containers next. Not enough to get R up and running in one of them with what you would need. That would require the tutorial that we are doing on April 2nd, I believe, that looks at some more sophisticated container workflows. But if you need to install R and dependencies in a way that makes Conda look appealing, I would consider a container-based workflow because it might be much more appealing than that even, is the new guidance I'd provide there. Is that helpful?
Yep. Thanks.
Yeah, absolutely. Other questions that folks have? Seeing and hearing none, we'll go ahead and continue. And like I said, we'll get just a little taste here of using some container-based solutions. So specifically, the piece of software that we're going to be using today for these containers is known as Apptainer, which was until recently known as Singularity, and there was a project fork, and we followed the fork that is called Apptainer. But it behaves identically for now until the forks diverge enough to Singularity. So any experience you have with Singularity or documentation you find about Singularity is very likely going to be directly applicable here, just so that we're all clear on the terms. And what Apptainer is providing as a container solution is a framework that allows us as researchers to, instead of building and installing software in a way that uses these sort of interconnected modules that we may load some from the system and some may be grabbed from the operating system. And we sort of have them all connected externally via environment variables. And it would be very difficult to, for instance, take our hammer module and copy all of the stuff that we would need and send it to a different cluster without rebuilding it from scratch. And what containers do is they take all of that, the software that you want to deliver, say Hammer, for example, all of its dependencies, and then package it up in a single file that you can then copy wherever you like, and it will, anywhere you have Apptainer installed, can use that file to run the software. You can think of an image file, which is the file that contains all of the software and its dependencies, as like a virtual computer disk that has everything we need to run our target software in it. And it's really convenient because it isolates the software from the underlying operating system in a very robust way. So for instance, if you wanted to bring the software to a cluster that runs a different flavor of Linux as their operating system, like maybe they're still back on Rocky, or rather on Red Hat 7, or they moved ahead to Rocky 10, as we may be doing in the not too distant future, um, you would be able to take that container and run it without too much worry on any of those systems without having to do anything to it aside from copy it there. Um, and that's very convenient for researchers who might be nomadic between clusters, who might need to share their workflows with other researchers, who might need to archive their workflows for later use. Just having everything in one file is very appealing for that. And yeah, we're going to look at how sort of the fundamentals of Apptainer work so that you can get some sense of how it could become involved in those workflows. And again, there's a lot more depth that we can get into with this approach to software that we will be looking at on the second purge. So we're still asking if you want to use Apptainer that you module load Apptainer. This is not strictly necessary at the moment, but it might become necessary at any time. Because we want to deliver Apptainer as a module rather than as something built into the system. Right now, it's sort of a hybrid situation. But for our purposes, module load Apptainer, please, and that will continue working the same in the future as it does now. And that gives us access to the Apptainer command, which we've currently got 1.4.5-2, which is pretty recent. And we can use this to obtain and run software. So we'll go ahead and I'm going to make myself cd back to my home directory. And I'm just going to make a tutorial test directory and cd into it, because I'm going to be generating some files in an unstructured way in this case, and we'll just keep those contained for my convenience. And as we like to do with many software frameworks, we'll start with a hello world example. And so what we're going to do in particular is we are going to use Apptainer to pull or download a CIF file. We're choosing the name of that file here. The singularity image format is what CIF stands for, I believe. And this is the destination that we are downloading to. So this file in this directory. And then we can point this to this URI, which is going to be singularity hub : //bsoc, and then hello world. And this is another one of those things where I have this in my notes, so I know it, but you would find this by browsing most likely Singularity Hub in a web browser to find the URI for the item that you want. The website there has a reasonably confident search, but we're often not interacting with Singularity Hub specifically, as we'll see in a little bit. But it is one place that you can go for some of your containerized software needs. So we've downloaded our image file here. We note that it is executable. And we can now run this with the Apptainer run command, conveniently named, and that will execute the default behavior of this image file, which, disappointingly to me, for a Hello World container, says rar avocado. It's from an earlier time when lol random was more amusing. But this is also what happens if you execute as a program hello world.sif. So Apptainer run hello world.sif is equivalent to running this as an executable file. Both of these are the same way of getting at that default behavior. And we want to know a little bit more about why this particular string is being printed out, we can say container inspect dash R to see what the default run script is for this. And when we inspect our image file, we see that it's this little shell script that runs so a bash instance inside of our container that runs this script called rar.sh, which presumably contains the text that we would need here. Now, let's say I want this hello world container to say hello world instead of rar avocado. I would like to use the software that's inside of here that allows it to print out text to the screen to do something different than that default behavior. In general, for doing that sort of customization of the workflow, we're going to use apptainer exec, which allows us to specify a command to be run inside the container. So we'll say apptainer exec, and we want to execute inside hello world.sif. And we'll say, I want to echo hello world, so that it actually says hello world as one of these examples ought to. And so what this does, although the printing of text to the screen is not a very impressive task for folks doing computational research, it is, our example here is using the text printing machinery inside of this image file to, instead of rar avocado, print hello world now. And we could compose any other command that is supported by the internals of this image file, which for our hello world component here is not especially interesting because it's a fairly minimal container that doesn't have a lot going on. But we could do things like print the date or other very basic Linux built-ins in here that happen to be contained. And if we want to explore the inside of the container a bit, like for instance, how did I know that this was bin echo that I had to point to? There's another command that we can use to get an interactive shell inside of the container context. So first, before we go inside the container, I will list the root of our file system outside of the container so that we can demonstrate what happens when we go inside. And then we'll run apptainer shell hello world.sif, and we have our prompts change. And then if we ls the root of this file system, we see that it is a different one. There are some elements in common, but things are different enough that we can immediately see, yes, this is a distinct environment in some way. And in fact, what's happened is when we enter into the shell session, or when a command is executed and then immediately exits, as we did with exec or with run, the context inside of the image file overlays and replaces the context outside of it for those commands that are run inside of our container. So for instance, when we ran ls before we entered in, we saw what happens on the cluster for that, where we see scratched up mobile projects, all the stuff that MSI has set up specifically. And then if we run ls inside of the container context, we see what the container bundled, including the rar.sh script. So we can see what's inside of that now, if we want to, which is just this echo command here, as we might have already expected. Now, this overlay does have some exceptions. There are certain device-related and system-related files and directories that are passed through so that the container instance can access resources outside of it, like knowing how to interact with the CPU scheduler or the kernel or such things. But that's that part of the pass-through is handled in the background, and we don't usually have to worry about it. That's certainly beyond our scope for today. Um, we'll look a little bit, yes, we'll look a little bit later at how we can intentionally bind an additional directory that might contain like our research data, like the input and output directories, into this context as well. But for now, we'll just acknowledge that they are not in there by default before we proceed. And we can say, for instance, which, okay. There's some funny behavior with which that happens inside of containers. Need to make a note to figure out again, and it's starting to happen again at this point. This was solved for a while, which is why I'm not anticipating it here. But there is some way that which is configured outside of the container that is being passed inside in an unexpected way, which causes it to break. So we can't, unfortunately, find where echo is defined using which right now. Tune in on the second when I will have this figured out. And we'll know how to get around that. But it's a particular peculiarity of the which command. Apologies for not having the solution immediately available here. Again, it was a surprise that came up today. But all right. So this was intended to just point out how I was finding the location of echo for this component, which doing so would require fixing which in this case. So that won't be especially convenient, but we'll be creating containers in a way in a moment that does not require us to know the exact path of things. So this will not be a huge problem for us as we move on with our material here. Before we look at making our own containers, however, let's look at a way to make a module out of a container. We like our module workflow. It's very convenient as a way of sort of swapping around pieces of software. And wouldn't it be nice if we could, let's say, module load singularity hello or apptainer hello, and then run a simple command to easily print raw avocado without having to track down our particular file here in order to do so, using the same convenience of the module system that we've seen so far. So to do that, it's a little manual and finicky, but it's not too terribly onerous to do for containers like this. So first, we're going to make ourselves with the -B here, because I'm going to create some nested directories all in a step. Say software.install. I'll call this. Note for myself to update a string there. Hello, and this will be 1.0, and then I want to have a subdirectory in there that will contain my image file. And then I am going to move the hello world file that I've downloaded into that directory so that it is stored within my normal software install directory hierarchy in a place that I can find it. I'm storing it in software.install because the image is the functional software that you actually run in order to achieve the behavior for the software. And if I hadn't already downloaded this, I could download it here and then move it, or I could CD into this directory and perform my pull there. Sort of dealer's choice on how you actually get the image into the image directory there. Then I am going to make another directory, which will be my bin directory, which I'm going to make alongside image, where I'm going to make some wrapper scripts that will utilize this image file to do operations that I would like it to perform. So if I do that, let me cd into it. And then I'll first make a script that all it does is run the default hello avocado printing behavior. They'll make a second one after that. We'll say nano, make a script called hello avocado. And we're going to make this an executable bash script. We'll change the permissions in a second, but we'll need a shebang at the beginning that specifies the executable that we want to interpret this script that we're writing. In this case, we would like the bash that exists in user bin bash for our purposes. And then paste in the location of my image file here. I'm assigning this to a variable called image, so that any commands that I compose using the image location are a little more readable. You don't have to have this big long string amidst an apptainer invocation. And then the actual command that I want this particular script to do is simply to perform that apptainer run command, which is the same as executing this apptainer run and then the location of the image file. And we'll go ahead and exit this. Hit Y to save that buffer. Enter to confirm the name. And then we will chmod +X hello avocado so that this becomes an executable script. Demonstrate that it works. We'll just run it right here before we create a module for it. And so now we've got this little wrapper script that sort of obscures any of the singularity complexities from us. We'll eventually just have a command that allows us to print out raw avocado. We might also want to have a more customizable command, as we had seen before. So we'll cp hello avocado to new script hello2, where we'll have a wrapper script that allows us to, on the command line, modify the output here. We'll say hello to whoever you provide as an argument. So yeah, we're going to modify this. We'll keep the image. Now we'll turn this into an exec, and we'll say echo hello, and then we will include this special bash character, which grabs any arguments that are provided after the name of our script here. So the behavior that we're going to target for is to run echo hello, and then we'll include some input inside of our hello world image. And that's sort of what we're wrapping around our image here into this hello2 command. And then we'll save our buffer, write that, and then we'll say hello to me. And it runs hello me. And because I use my greedy bash argument thing, it grabs every argument that's space separated. I'm going to say hello everyone else as well. So Not the most fantastic commands, but close to limits of what we can do with the hello world image that are appropriate and interesting. So we can now make ourselves, we don't need a dash p here, in our module files .local, we'll make ourselves a directory called apptainer hello. Let's say module files .local apptainer hello. We'll creatively name this 1.0 as well. And then we will extra character in the magic cookie there is no good. This will be my home directory. Install hello 1.0 /bin, which is the location that we put those wrapper scripts. Then we'll go ahead and save our buffer there, the file name. I'm going to CD so that we are no longer in that directory, so I can show there's nothing up my sleeve with respect to referencing those files locally. And now I can module load apptainer hello, and I can say hello avocado, or hello to whoever I like with those two wrapped commands. And you can sort of see the shape of a module file creation workflow that could be useful here, where you use these wrapper scripts to contain a particular way to run a particular image file that you then essentially wrap in a straightforward command that you can access via module load and then running that command. Can be a little more convenient than having to compose these apptainer commands on the fly, especially if you are like managing a set of container-based workflows for a group or project, for instance. Not everyone's going to want to learn how to use apptainer, but you can sort of bottle things up in a way where they don't necessarily have to look at it if you want to do this little bit of orchestration. Folks have questions about this approach before we move on to a little bit more for apptainer?
I had a quick question.
Yeah.
So containers are new to me. So you described it as a sort of a computer desk. So it's sort of like an environment where you create an environment with all of the software and functions that you need to use for a specific program. Is that the idea?
That's the idea. And that goes so far down as to include most of an operating system in a lot of cases. Like we'll see in a moment, we bootstrap from other container files that contain like most of Ubuntu or Debian Linux. So it has all of the dependencies down to a fairly low level, and then all we're really getting from the host system, the cluster here, is interfaces to the devices via the kernel. But everything from that level up is intended to be included in this this sort of virtual disk file. And if this is of interest and thinking about this in a little more detail, in this kind of format is of interest, we do discuss this in more detail on the workshop on the 2nd. Other questions about the containerization approach that we're looking at here? If not, go through a few more of the sort of must-know components here. in the time we have left. Uh, so let's CD back into my tutorial test. And so I don't have that .cif file here anymore. So let me download it again. .cif from, so I already have Sonic. And instead of giving us a download progress bar this time, it's saying that it used a cached image, which indicates to us, uh-oh, AppDanner is caching things like Conda did, and we may have to pay attention to that. And indeed, now, AppDanner is very good at generating many gigabytes of cache that can fill up your quota fairly quickly if you're doing diverse workflows with it. So there is the AppDanner cache subcommand. You can say AppDanner cache list to specify what's currently there. I don't have much at the moment, only just this one gigabyte spread across a couple of different components here. And if I was curious about specifically where those came from when they're created, I can add the -b flag to be a bit more verbose. They're unfortunately named using these sort of SHA-SUM, I believe, naming schemes. So this is not as useful. We can see the type of thing that they are, and we can see the size that they are, and we can see when they're created, which may be useful information for determining what we need to keep versus not. We'll go a little bit more in depth with this if we need to sort of selectively prune things out when we look at this in a couple of weeks. But for now, being aware that there is a cache and that we can AppDanner cache clean to clear it out if we need to. Unlike with Conda, clearing out the cache will not have any effect on any container files that you already have in your possession. So I can very comfortably say, clear this out now, and have every confidence that my hello world.cif is going to work exactly as it did moments ago, as will any of my other CIF files that I have stored in their useful locations. So my general approach with the cache is I keep it active if I am developing a new container where I might need to rebuild it a few times until I get something that works. But once I'm done with that, I will freely clear it out because all it really does is save me download time and save the developer servers their upload bandwidth. So there's no use in keeping it indefinitely around because it sits there unused unless you're actively building against it. If you are doing some workflow that requires you to keep the cache around for longer, there is the AppDanner cacher directory, which you can set to something else so that it's cached in like global scratch or in your project directory as is appropriate. But this is less commonly needed compared to a Conda cache modification. So we had already seen if we run ls inside and outside of our container environment that we get this different view because the container is essentially overlaying the file system that exists outside. And this is great for providing dependencies in a way that doesn't allow other things in your system from breaking them. But you need some way to include your input data, right? So to do that, we can use the -b option for our various AppDanner invocations to bind a location from outside into inside. So for instance, with my exec here, I can say -B, say scratch .global if my data that I'm working with lives on global scratch right now. And this will bind that directory from the host to a location of the same name inside the image context here. So if I do that, I see scratch.global shows up, and I can see my subdirectory within there if this is where I was storing my particular data. We can see a couple of CIF files living in there that I've shared out to folks using this approach. Now, sometimes you want to bind a directory to a different location inside of the container versus out. And we could, instead of calling this scratch.global, this could be data or some other directory name that we choose. I'll call it my research data, so it pops out a little more on the LS. But we can see now scratch.global is not visible in the container context, but my research data is. And if I put down 404, this just bound scratch.global to this different location. And you can bind subdirectories as well. If I wanted to directly bind scratch.global / Dunn 404 to my research data, I could do that, and it would just change the relative path here. And AppTainer has some good documentation about how you can use this -b, and then actually a couple of environment variables as well to modify what is bound by default into your container contexts. But we'll just stop at pointing that this exists here for today, and leave it either to your own reading or to following up in 2 weeks to see more of this. Another thing that I will flag right off the start here as one of our important basics is that while we can pull from Singularity Hub as we have been, perhaps more importantly, we can pull from other repositories like Docker Hub. Docker is an older and more popular container platform. And so, for instance, we want to pull an old version of Python from a Docker Hub repository. We could do this by specifying what we want to download to, and then we access Docker Hub via the Docker prefix for our URI. But then it works very similarly to what we had seen for Singularity Hub, where we're adding a little bit of additional syntax here, where Python is the project name on Docker Hub, and then this is the tag for the particular project. And you'd get that information from looking at Docker Hub to see what tags were available and which one you wanted to grab. And it downloads different components. Docker images are provided in layers, not quite the same format. So there is this conversion step that needs to happen. You'll almost always get these warnings, but they're almost never important. And after a short wait, the AppTainer file is created, and we have a from Docker Hub Python 3.9.6.cif image that we could use. And there's all sorts of stuff available on Docker Hub. That's where the vast majority of research containers exist right now. And you can also grab things from NVIDIA's NGC catalog. That URL is a little more difficult to find. So I'll just post that in chat. If you want GPU accelerated software, then that is already sort of built for you. Then the next thing that I would like to do is demonstrate how we would build a container of our own that fits our particular research needs using a definition file to do so. So we'll open this up. We'll say this is ubuntu.def. So we're creating a text file where we're going to use our special def file syntax to specify how we want a container built. And I'm not we're right at the end of time here, so I'm not going to have the opportunity to type it out or to walk through the entire logic. But this example that I'm using here is one that we worked through with some specificity in 2 weeks. So we'll go ahead and paste it in so we can at least get a taste of what's going on. Ooh. Don't be like me, kids. I've messed up scroll behavior on my terminals. But all right, so basically what we're doing is we're bootstrapping from a pre-existing image. This from Docker, there's an Ubuntu 20.04 image that we're downloading to start. Then we're installing some additional software on top of it, including our Hammer example that we had seen. And we do this a little bit differently here. We modify the eventual environment of the container context so that it knows where we've installed Hammer, so that we can conveniently use the Hammer command without Hammer commands rather, without needing to specify the full path to them. Provide some default behavior using a run script. Give some meta information about the container, and then we're also able to provide some help documentation if we want to. And again, this has gone through in a lot more depth in the Apptainer tutorial in a couple of weeks. But for now, pointing out that these things exist and that we can use this to say Apptainer build hammer.sif hammer in ubuntu.def. And then the behavior that we specified inside of our def file is done. So using the Ubuntu apt package manager to install some dependencies. And we're able to sort of engage with that Ubuntu instance as if it were sort of its own independent operating system within this virtual disk. Then Hammer is being built as we had seen it before inside the container. And then in a couple of moments here, we will be left with a CIF file that we can use, just like our roaring avocado example, hello world, except it would do Hammer-related research tasks. And it should take just a moment to complete as the source code is compiled. Almost done. There we go. And then it finally creates a CIF file from this, which it says will take forever, but it speeds up fairly quickly after a certain point. While we're waiting for it though, so this is my very cursory look at sort of the bread and butter approach for using Apptainer, either identifying an existing container from one of these repositories that does what you need, or making your own via this build from definition file approach. Then you end up with these CIF files, which you can define a default behavior for, which in this case was the help for nhammer. Or you can let's have it do something different. We'll do hammer-h. We're going to bother running exec. If you want to use exec to run a custom command. For a custom container that we built with our custom software. So you can get really powerful with your customization for these container files. But we are over time. So we'll stop here. We'll just consider this a preview for further Apptainer work for those folks who'd like to join us on the 2nd. but I am able to stick around a little while for questions if folks are also able to and would like.